Hello everyone, my name is Jeremy and in this video I will show you how to explore CPython bytecode in Jupyter Lab. This is a presentation I originally gave at the Python Pizza Berlin conference that took place about a week ago. That was on February 23rd, 2019. And this is a video for those of you who couldn't make it to the conference, but also for anyone interested in the topic. So let's get started and let's look at what Jupyter Lab is. So Jupyter Lab is the next-gen UI for Project Jupyter. You can still work with notebooks in Jupyter Lab the same way as with a classic notebook interface, but Jupyter Lab is a bit more like an IDE and a web browser. There is the notion of a file browser as well as a command palette. One can search for a command and execute it right away. For example, here we're starting a new console. And the main idea behind Jupyter Lab is that everything is built as an extension, which makes it easier for third-party developers to make their own extensions. The reason I wanted to mention that is that in a few minutes we will see one of those third-party extensions. Okay, so let's move on and let's look at what CPython bytecode is. So CPython is the C implementation of the Python programming language. So Python as a programming language can be implemented in many different ways. And CPython is the version you get from the python.org website, for example, and also the one I shipped in many different Linux distributions. When we think about Python, we usually think of it as an interpreted language, which is true to some extent, but if we look at this diagram, so this is a simplified version of what is happening under the hood whenever we want to execute Python code. So we see that before the code is being executed by the Python virtual machine, there are actually different steps involved. And one of those steps is about generating bytecode right here. So we are not going to go too much into the details of what the CPython interpreter is doing and what the CPython bytecode, how it gets compiled and so on. For that there are a lot of resources online and they are really good, so I recommend you to check them out. But in our case, let's just start with an example. So let's say we have a function called add that takes two parameters and adds them together. So if we try it with two integers, we get the expected result. Now let's look at this. So import this. Import this will mean that we're going to import the this module from the Python standard library. And the this module also has a function called this. So if we call it on a previously defined function called add, we see that we get some text back. And this text is a text representation of the CPython bytecode. We find A, B, which correspond to the parameters we pass to the add function. But there is also the notion of this binary add instruction, which will correspond to this plus operator. Okay, so we already have a way to look a little bit under the hood and have an idea of what the CPython bytecode is by using this module and calling this method. But what I want to show you today is another way to look at the CPython bytecode, and for that there is an extension for Jupyter Lab called the Jupyter Lab Python bytecode extension, which is available on GitHub. And if we start from an empty Python file, we do a right click and show Python bytecode. We get a little prompt to select the kernel we want to use. So let's go with the default for now. And we see that we already get some bytecode right here for empty file. And now, as I type, we see that the bytecode view is automatically re-rendered, so we get a live preview of what the bytecode for this Python code is. Alright, so I can move the cursor around and a different line will be highlighted. Can also have multiple cursors right here. That can be useful, for example, to highlight a specific part of the code or of the bytecode. Another interesting feature is the fact that if we go back to this little prompt here, we can actually select a different kernel that will be running a different version of Python. So in our case, let's choose 3.8. We see that the CPython bytecode is identical, which is okay for this example. But what happens whenever we actually use a feature that is only available in one of the versions? So with this code snippet here, we are using the walrus operator, which is a new addition, to the 3.8. And we see that 3.7 is unable to parse it, returns an invalid syntax instead. But for the 3.8 bytecode output, we actually now know pretty easily what the bytecode is for this walrus operator. Okay, so that was a little overview of what the extension can do. Now we're gonna look at a few examples to see how we can put that in practice. Alright, so the first one is about loops in Python, and this example comes from this article about the Python bytecode. So let's open this file. Let's open the bytecode preview. Alright, we see that we have a while loop which defines its own counter I and increments I at every iteration. I think we will all agree on the fact that this is probably not the most Pythonic way of writing a loop. So for that, we can create a new Python file. Let's pull it to the side, and let's also open the bytecode preview. Alright, so now we have side-by-side comparison of two Python files, and let's try to write a more idiomatic and more Pythonic loop. So let's use the for in range structure. What we can directly notice right now is we're still doing 10 iterations, but now the bytecode that is generated is quite different. We can notice that for the for loop, this is actually much shorter. What it means is that the Python virtual machine will have to execute less instructions. So in a way, this can be considered as a more efficient code. So it doesn't mean necessarily that because there are less instructions to execute that the code will execute faster. But in this case, we see that first, this is a more elegant way to write a loop, and second, it compiles down to a shorter bytecode. Alright, so the first example was about comparing two different styles of writing a loop and see how the number of instructions differs. The second example will be about comparing the instructions themselves. For that, let's look at an example about globals and what we can call optimizations in Python, which also comes from the same article. So there is this first code snippet which defines a compute function and iterates 1,000 times to add this result from this math.sign call. And the second one does pretty much the same, except that there is an extra line right here which caches this sign function, and then this local sign function is referred within the loop. Okay, one more time, we can compare them. And we might wonder, like, why is the second code snippet like this? Why would we need to do something like this? This version, one could argue, is more readable. Well, let's look at how they perform in terms of efficiency and how fast they execute. So let's load them. Let's look at the source code one more time. So now we can have them all together in this output cell. And let's time the first function, and also let's execute the second one at the same time. Alright, so we're gonna get a little benchmark of how this function is performing, and then we can compare it to this one. That we can get some numbers in how fast they execute. Alright, so there we have. So there is one of them that is much faster. Well, maybe not much faster, but at least there is a little gain in terms of performance. and this is actually the one that does this little caching trick right here. So we have a way to measure this difference, which is by doing this little benchmarking right here. But now we would like to know really, like, can we explain why this is happening? And for that, we can go back to putting the two files side by side and looking at the underlying bytecode. Alright, so let's also open a preview for the second one. And alright, now they are nicely aligned. If we put a cursor on this line, we will see, alright, that okay, the first thing we can say is we are within the loop, and within the loop there are a few instructions that get executed. Alright, so they are all mentioned right here. And one of them is a load global, which is used to know what math corresponds to. Okay, let's do the same on the other side. Okay, let's put a cursor right here. We see that we still have the load global, right, to know what math refers to. But we are looking only at the line number 5, so this one. And now if we look at the loop itself, which is right here, let's put the cursor inside. We see that this is not the same set of instructions being executed. And one big difference is that whenever we call the sign method right here, so instead of doing a load global and then a load method, we have replaced that by a load fast. So we have somehow managed to take this load global and put it one more time outside of the loop right here, and within the loop this has been replaced by a call to a load fast. Alright, so this is the main difference we can notice between those two code snippets if we look at the bytecode. And this is actually a way to explain these time differences we saw when we were doing the benchmarking. Because as the name suggests, a load fast will actually be faster to execute than a load global. So it might be a little bit like a guess or a little bit more difficult to really know why. So there is always one more thing one can do to make sure this is the case, and this is about going back to the source code. So what we've seen is that not all bytecode instructions are equally expensive, and we can look at it by looking at the ceval.c file that is part of the C implementation of Python, so the CPython implementation. And in this file, we see that there are different case statements for each of these bytecode instructions, and the one for the load global looks like this. Alright, so there's quite a bit of code, and the comments actually say that several namespaces are being searched. So what it means in the end is that it's kind of going all the way up just to find a specific name. And if we compare that to the load fast instruction, we see that first there is much less code, and instead of going in all of the namespaces, there is a call to this macro here, the getLocal, which is in the end going to be about indexing into an array. And this is another way to somehow explain this difference we noticed. Let's go back to this benchmark right here. The fact that a load fast will be more efficient than a load global to execute. Alright, so there is so much more to talk about when it comes to CPython, the CPython interpreter, how it works, and also about the CPython bytecode itself. There are a lot of references already online, and really the goal of this video was more about showing you how to do it with this Trippy Lab extension. So feel free to check it out. Again, that was like the goal is to provide a different way of looking at the bytecode, so without having to do this import this and then call the this.this on a function, object, or basically anything. And then there is this nice little feature of getting this live preview, so you can also start typing Python code and see how the bytecode is generated. All of this, of course, to kind of provide this interactive exploration feeling, which can be very important for educational purposes. Alright, that's pretty much it. I hope you enjoyed and thank you for watching.